Today we're going to take a look at different similarity criterion for triangles, and we're going to get into the idea of how could I prove triangles similar. So this first problem here, it says we're given the fact that the triangles actually are similar. Given triangle ABC is similar to triangle DEF, we're going to show why only two pairs of congruent angles are needed to prove them similar. Okay, so notice that angle B is marked congruent to angle E, and angle A is marked congruent to angle D. So we already know that they're similar. I only need those two angles. We're going to take a look at that. So this first statement, it says, what is the similarity transformation that would map ABC onto DEF? So with that in mind, this would be like considered our pre-image, and then this would be considered our image. So I'm trying to transform ABC, map it onto DEF. And in general, if we were to just take a look at it without all the technicality behind it, we could say, well, definitely a dilation has to happen. And probably some sort of a rotation so that I could get B to map onto E and A to map onto D. So just to be maybe general, we're just going to say a dilation and a rotation. Now the scale factor for that dilation. Okay, so we have said in the past, if I wanted to find a scale factor, I would think to myself, it would be the image divided by the pre-image. So if I took any segment in that image, so for instance, maybe I'm going to take segment DF and divide that by the corresponding segment in my pre-image, that would be AC. So DF divided by AC, that would be our scale factor. Now, it says, let's show a sketch of the dilation. So we'd have to pick a center point. And when we're doing our dilation, again, as long as I state where we're going to do the dilation from, it does not matter. So it could be from B, it could be from A. I'm going to take and dilate it using the center at A, which means if I were to dilate it, and it has to get smaller, that means the segment BC would move up and closer to the center of dilation. So let's say, for instance, here's my B prime, C prime. Now keep in mind, when we're doing this dilation, our sides are always in proportion and our sides are parallel. So with our sides being parallel, even though we've done this dilation, this angle B does not change. So that's still the same angle B that was the angle B from the original shape. Okay, and so now it's saying, so what's the relationship between the dilated triangle, triangle ABC and triangle DEF, and how do we know? Well, I have to say they're similar. They have to be similar. Okay, how would I know? Well, like we just said, sides are in proportion. And I know that because a dilation will keep sides in proportion. And I also know the angles are congruent because, again, a dilation will keep our angles congruent. It does not change that. So I could say here, a dilation is a similarity transformation. This is what we did in our last unit. So I know that they have to be similar. But then if I took a look at that second one that we did, so once I know my sides are in proportion, angles are congruent, once we did our rotation is a basic rigid motion. And we know that that means it does not change the size or the shape. So once we took ABC and shrunk it down to be the exact same size as DEF, I still had to do a rotation, but a rotation being a basic rigid motion, it's not going to change the shape or size. So therefore, I could show you that those two triangles could map one right on top of each other. Okay, so again, going back to, well, what were we given? What did we need to prove them similar based on what was given? Only information we needed to prove them similar is we needed two congruent angles, which brings us up to this angle-angle theorem. So the angle-angle theorem states that if I have two angles of one triangle and they're congruent to two angles of another, the triangles are similar. So here's a way that I could prove triangles similar. Okay, so looking at question 2, maybe throwing some numbers at it, it says, as these two triangles are marked, would it be possible to prove them similar? So I need to find the third angle in each triangle. So if I'm looking at this triangle on the left, I know there's 180 degrees in each triangle, so I'm going to remove the 40, I'm going to remove the 100, and what I'm left with is 40. So this missing angle down here is 40. If I do the same thing on this triangle on the right, 180 degrees, remove the two angles that I already have, I'm left with 100 degrees. So I'm looking here and I can say, so that angle is 100. So in order to prove them similar, I only need two angles to be congruent. So I can look and see, well, angle 40, I have an angle of 100, there's my two angles, that's enough. And now, I'm sorry, I said congruent earlier, similar. I have enough to prove them similar. So I could say, yes, they are similar. So triangles are similar, the one squiggle, that's your similar symbol, and I can say by that angle theorem. Okay, and notice if two angles of one triangle are congruent to two angles of another triangle, well, then the third has to be congruent no matter what, automatically, which is also a nice little theorem that's called your third angle theorem. Okay, another way that we can prove triangles similar is the side angle side, but it's for similarity. So this is different from side angle side when we prove triangles congruent. So let's read through and see the difference. So if an angle of one triangle is congruent to the corresponding angle of another, and the lengths of the sides of the including angles are in proportion, then the triangles are similar. Here's our big key difference. It's not that the sides are congruent, but the sides are in proportion. So side angle side similarity, angles are congruent, sides are in proportion. If I were to summarize that, I'm going to say angles are congruent, sides are in proportion, and this should sound very similar because that's exactly what we said was going to happen when we did a dilation. Okay, so with that in mind, it says, as marked, would it be possible to prove these triangles similar? So the triangles we're trying to prove similar would be triangle PQR and triangle PQ prime R prime. So I can see little triangle, big triangle. So the nice thing with them, if I take a look at the two triangles, they're overlapping. And with them being overlapping triangles, that automatically gives us that congruent angle by that reflexive property. So I could say to begin with, angle P is congruent to angle P, and that's our reflexive property. So then the next thing I need to do is check our sides and see, are they in proportion? So I'm going to compare side PQ and PQ prime. So staying on the left side of the triangles. And I'm going to see, is that in the same proportion as when I compare PR to PR prime? So this is our question. Okay, and if I were to make that proportion, PQ is 3. That whole length from P to Q prime, that's not only the 3 from the top, but the 10 on the bottom, so I'm going to get a total here of 13. And I'm trying to see, is that the same proportion as when I compare PR, which is 2, to PR prime, which is 2 plus 7, so a total of 9. So two ways you could test this. You could type this into your calculator and see what each of those fractions reduce down to and get decimals. So if I did 3 over 13, I'm going to get 0.2307969, somewhere around there. And if I type 2 divided by 9 in my calculator, I get 0.2 repeating. These two things are not equal. So that's going to tell me my sides are not in proportion. Okay, that's one way to test. A different way to test is you could cross multiply these. So if I did 9 times 3, so 9 times 3 would give me 27. If I did 2 times 13, that gets me 26. And again, I see they're not equal. So is it possible to prove these triangles similar? No. And our reason, our sides are not in proportion. Okay, and then we get a third method for proving triangles similar. And that's our side, side, side similarity. So very similar to what we did up above. It says if the three sets of corresponding sides of the two triangles are in proportion, then the triangles are similar. So again, that's our key phrase there, is that they have to be in proportion. So we're going to check and see if these two triangles have sides that are in proportion. And like we did up above, I'm going to do something like, let's compare AB to A prime B prime. So AB I see is 1.41, A prime B prime I see is 2.1. And if I were to reduce that, type that in my calculator, get a decimal, I'm going to see it's approximately 0.6 repeating. Okay. If we try, let's do AC. So AC compared to A prime C prime. Okay, so AC is about 5.25. A prime C prime is about 7.28. And when we divide that out, we're going to get about 0.721. I can already see these are not equal. Okay, good idea to test the third. And if we do that, we're comparing BC to B prime C prime. So we have 6.04, and I compare that to 8.29. And again, if I calculate that out and get a decimal, I get 0.7286 approximately. So none of these sides are in proportion. So if they're not in proportion, I can say my triangles are not similar. Okay, so what we've just figured out is we have three ways that we could prove triangles similar. We have angle, angle, we have side, angle, side, and we have side, side, side. And again, anytime we're talking about sides, we're saying sides being in proportion. Okay, so if I can prove them, if I have theorems to prove them similar, we are going to try and do some proofs. So just like our other triangle proofs, we're going to start this off by writing down our given, marking our picture, seeing what we have, and then going from there. So our given information right now is telling us that we have some perpendicular lines. And what we're trying to prove, it's always a good idea to know what you're proving, is triangle UXV. So triangle UXV, so this one here, we're trying to prove is going to be similar to triangle WYV. So WYV. And what we've been given is the fact that we have perpendicular lines. Back when we did congruent triangle proofs, we know perpendicular lines form right angles. So it'd be a good idea to take the right angles in the triangle. So for instance, this angle and this angle. And you first, remember, have to state that you actually have right angles. So I'm going to say angle VXU and angle VYW are right angles. And we know this because we have perpendicular lines form right angles. Okay, and in our triangle proofs, we would always say, well, once I know I have right angles, I know that they're congruent. We are always looking for congruent statements. So I'm going to say, okay, angle VXU is congruent to angle VYW. You can say here because all right angles are congruent. So from just our given, what that's telling me is, and keep in mind, we had three ways to prove triangles similar, either angle, angle, side, or side, side, side. And these were all saying that they were all similar triangles, right? Sides being in proportion. From just knowing the fact that I have one set of angles congruent already, that means I'm probably not going to be doing this side, side, side one. The other train of thought is I really don't have measurements for the sides of my triangles. So that's really going to be difficult to try and show the sides are in proportion. So that would make me think, let's try and find a second angle to prove congruent, because if I can, I could prove my triangles similar. And if I notice that my triangles are overlapping, I can see up on top, they both share that angle V. So I could say angle V is congruent to angle V by that reflexive property. And now we have two sets of angles congruent. Remember from that first problem that we looked at today, as long as I have two sets of angles congruent, that's enough to tell you my triangles are similar. So we have our proof statement, triangle UXV is similar to triangle WYV, and our reason here is just angle, angle. So that's the beginnings of looking at proving triangles similar and taking a look at the 3 different theorems that come with that. Hope this helped. We'll do some more in class. Don't forget, like and subscribe. Have a great day.